Thank you for giving me this opportunity to inviting me to give a provocative talk of how Reanalysis Enterprise might change in the era of machine learning models. This has, as you will see, this conversation was informed by a lot of people, so I can't credit every single person, but I'll credit our community at large. So all good ideas go to the community. All bad ideas, I'll take blame for them. Okay, so I'll start by presenting 5 perspectives, because like you walk around and you talk to people, and they all have these different perspectives, and they're evolving over the last year. So about a year ago, this science paper came out from Google DeepMind, and essentially the quote from the leader of that group is, "GraphCast would not be possible without Era 5." And like he's adamant about it. They're like, this was really important. Like, would not be possible. So a possible conclusion is that all we need to do is to produce the best possible reanalysis Era X. And corollary to it, if you're not providing the best reanalysis, should you even try? Like give up. Like let Hans do it. Okay, so 6 months later, this paper from Microsoft Research comes out, and it's called this Aurora Foundational Model for Atmosphere. And this, I'll walk you through this graphic on the left. But the statement is, we demonstrated that training a large model on diverse data sets improve atmospheric forecasting. So let me walk you through it. So if you train a model on only Era 5, it's a blue line. If you throw CMIP in addition to Era 5 and IFS high-res, you get a yellow line, like a tiny bump, just slightly better, right? If you, but if you take yellow line and add GFS, just a little bit of GFS data to it, you get this dark orange line. So the biggest reduction from blue to orange is from adding just a handful of years from GFS operations. So the take-home message from it is that diversity of model dataset is really has never been a time when diversity of datasets was as important as it is now. Even adding GFS data, which is not as good as IFS HR, is amazing. Like it makes models better. So that's one perspective. And then perspective 3, there was this paper called Aardvark Weather, and they said well, we don't, to be cute, they say it takes raw observations as input, provides forecasts directly. No model initial condition is needed. If you read the papers, they actually do use models that precondition their forecast on Era 5. But essentially what it says that in addition to model data sets, observational data sets, exposing raw data from the reanalysis community to the wider enterprise is important. We have 2 more perspectives to go. So perspective 4, we had this workshop on how NOAA enterprise is going to change in the face of these models, and the same very famous person from a very large tech company came in and says reanalysis will become obsolete as we teach models to learn directly from data. And well, that's a big statement. Can you imagine this person? And this person would stand right here and they'll tell it into your face. And luckily we had another person from the reanalysis community that kind of in a moment was able to say that, well, reanalysis is an essential climate data set that has many unforeseen uses beyond serving as a training data set to AI models. So that whiplash that we all experienced a year ago was well, reanalysis, the most important use will be AI model training, and then it's all AI models. No, providing a climate record is very important, and we should not lose track of that. So my last perspective was this challenge from Tony McNally's, what's our end goal? What's the end game for machine learning? So I'll try to answer Tony McNally's challenge. So I'll give 3 scenarios. Scenario 1, investment into better traditional reanalysis. Scenario 2 is making the reanalysis tent larger and increasing diversity of reanalysis-like products. And scenario 3, I'll try to speculate what the end game might look like. So we all know that when ERA 5 was produced, it was a major step compared to ERA interim, and there's this famous plot from ERA 5 paper. And the path forward, as we have seen from this week, is that we're going to increase the resolution globally and locally. We're going to go coupled. We can improve data simulation complexity. We can have more reprocessed observations and rescued observations. And the world wants us to provide it in a better storage format. The caution, of course, that the cost of producing this reanalysis is so expensive that we're very conservative about it. So we produce a new iteration every 7 to 10 years, and that maybe that should be reconsidered. And it makes us risk averse. We're not investing enough into kind of rethinking how it should be done. So just a quick summary. So if we think about the scope of different reanalysis, we had a workshop on it a couple of years ago in the US to kind of think about what the suite of reanalysis we need to produce. And with the feedback from our European partners, it was very helpful. Thank you for participating. And with input from NASA, as you guys saw this morning, for talk from Amal, as represented by Steve, that essentially the story is that we have this evolution of the observational record. And this evolution of the observational record dictates which reanalysis you can produce. And that was my comment earlier today, that there's no sense in producing 1/12 degree reanalysis for the ocean in 1950s. It's just not supported by observational data. And based on the length of reanalysis, there's also this interplay of different user communities, from climate to energy and infrastructure. The caution is that if all we do is to continue business as usual, the progress in reanalysis has been driven by the Moore's law. So if you line up the cost of producing reanalysis, it kind of falls on the Moore's law line, and a few of them go beyond Moore, but none of them actually goes above Moore's law. But what happened in the deep learning literature is that they broke the Moore's law in around 2010. They accelerated past it. So as a community, we owe to our users how to figure out how to use that acceleration of compute. So let's switch to scenario 2, invest in diversity of training data sets. So I'll talk about specific approach that we're taking, because we're still, takes us a long time to prepare for no reanalysis. So we invest into this UFS replay data set that's been very useful to us. I'll talk about the Ninja observational archive that will provide observations for machine learning training and for reanalysis, for non-nascent reanalysis. There's a lot of regional downscaling efforts like CONUS 404. And I'll talk about the need for shorter and more frequent reanalysis. So Gil did a great job of summarizing the replay methodology, and it was also mentioned by a NASA talk. I'll not go into detail what replay is. It's already been covered in this meeting. But the benefits of it, it's a very realistic simulation, as you have seen. And it generates additional output that we might want to use in training. So for example, we're able to generate model level data because we know that the type of emulators we want to train them on model level, not on Z level. And it also, can generate a lot of diagnostic output that was not available for us elsewhere. Switching to observations. We're in a multi-year project collaboration with NASA and produce a joint archive for reanalysis, and it will be a comprehensive archive of atmosphere, ocean, ice, and land observations going back to 1979 and extending into near real time with a 2-day delay. It includes a satellite black and white list. Right now it has a variety of file formats, but we're working with a non-profit to convert this archive into AI-ready format. And there was a poster by Jessica Knesha earlier today on this subject. Final perspective on the diversity of data sets. There was this paper that was pretty obscure paper in the machine learning literature, one of those multiple papers that came out last year. But essentially what they did, they trained their model on 1 year of data, and they trained it of era 5 from 1980s through present day. And not surprising, if you train on 1 year of era 5 in 1980s, RMSE is actually quite bad. It's like almost 50% as bad if you train it on the most recent data. And of course, this community understands that that's because there is many more observations that go into reanalysis after a year 2000. So one can see that one thing that the world might want from us is that in addition to generating these amazing climate records, like era 6, that's going to go back to 1950s, maybe what we also need to do is to generate much more frequent reanalysis that are shorter, maybe 5 years, maybe 10. I don't know what the appropriate length of record is, but it's somewhere within 21st century. And maybe doing that every 2 years is more important than making a perfect reanalysis every 10 years. So finally, going to the speculating about the end game of where all this enterprise is evolving to. In a lot of variables, there is a lot of consensus between reanalysis, and we saw that today. And for some variables, there is no consensus for reanalysis. The reanalysis is hugely biased. So I picked one of those examples. So it's a high cloud cover as detected from MODIS, era 5, era intermediate, era 2. And you could see that, all the reanalysis do know where subtropical gyres are located and where the convergence zones are located. So that, that's not surprising. But the biases are huge. So if you try to train machine learning model from this data that will predict cloud cover, it will be terrible. Like, you should not do that. So how do we reconcile that? And if similar story can be told about precipitation to meter temperature. So one thing that these ML models are actually very good at is that they can beat long-standing biases. So for example, here is this coupled models that kind of geared towards answer forecasting. So they're training in a model that only knows about 24 to 48 hour tendencies. And this from 24 to 48 hour tendencies of a coupled state, they can train something that is competitive or even better at El Nino prediction compared to like GFDL model. And GFDL model, very similar to the rest of the model, it has this persistent biases, like this bluish color. Like you can see that it's like always wants to go too negative on the answer. And in contrast, this very simple ML model that they put together, like has no visible bias. It's like it's amazing. We couldn't have solved. We've been working on this problem for 20 years, and then somebody comes in and solves a lot of this bias in about 1 year. So another thing that some speakers, not on this stage, but we talked about at this conference, and there was a poster about it yesterday. The way we do reanalysis right now is suboptimal. And essentially what happens is that they build on the tradition of filtering solutions in NWP. So in WP, you don't have observations for the future. So you're using all observations until the cutoff to produce the best analysis condition at the end of the cutoff to produce a forecast. And that's what you do in era 5 or any other reanalysis of like atmosphere. You use observations up until the end of the window. You produce the background for the next one that gets improved by observations in this window, and you go so on. What you don't do, you don't take observations from the future, which in the reanalysis mode, to improve analysis for the previous window. Like, for example, like this concept. And the way it shows up, there's this paper from University of Washington that it's not a paper yet. I think it's just a preprint at this point. But there was this phenomenal heat wave in Pacific Northwest. Pacific Northwest got hotter than the Death Valley. And the 10-day forecast was not good. It had no heat wave whatsoever from that initial condition in era 5. What they have done, they run the adjoint of a machine learning models 10 days backwards, something you cannot do with traditional model. And they said that like you can actually adjust, knowing that there will be a heat wave, you can back propagate it to an analysis state 10 days beforehand and produce a better initial condition that can actually is reflective of this precursor to this heat wave. So I'll make a wild speculation that's my last slide, what the end game might look like in this era of ML models. So we still have our physics models. Have such a richness of information to them. And we have our observational record, which we need to keep improving. And we produce our traditional reanalysis. But that's just a first step. That's a first guess for what a reanalysis trajectory is. And then, we can train our deep learning model on it. But then we do a joint estimation of reanalysis trajectory and model weights. And I think we don't know how to do that yet. But that's what needs to be done. That's the step that can try to remove the biases that we're stuck with right now, because we're not making our progress fast enough on traditional models. And that's my conjecture that will be one way to go. And if you were last week at ISDA meeting where were a bunch of data simulation people, what they also want to do in this step, they also want to learn a fast approximator for data simulation step. Because the conjecture is that in operations, we can drastically lower the cost of data simulation through this approximation step. It doesn't help us to develop a better data simulation, but it will be very useful in operations. So to kind of summarize my thoughts in relationship to Tony's question was traditional investments in better analysis should continue. We need to do better observations, improve model complexity, resolution. We should invest in reanalysis research. I think we're so bogged down into producing reanalysis that we're not investing into exploring new ideas of how to do it better. The reanalysis tent can get bigger. We can increase diversity of reanalysis, right? Like product. We can make data ML ready from the get-go. It's actually, but as many of you know, the best way to access era 5 is from Google. It's not from Copernicus. And we should probably increase production of some of the reanalysis products. And my conjecture to the group is that I think the end game is that we produce an even better reanalysis and a better models by this joint estimation. So that's it, and we have plenty of time to for people to question my provocative statements.
Thanks, Sergey.